Okay, new unit, unit 10, stoichiometry. Cool word, right? Stoichiometry. Go home and tell your parents, I learned about stoichiometry, or just throw it in randomly, like, how was your day? Stoichiometry. Just cool stuff. I think it's cool. But what does it mean? Well, of course, leave it to the Greeks that we copy all their words. They come up with all the good stuff. Stoichion, meaning element, and metron, meaning measure. So stoichiometry is we are measuring elements. Here's the chemical or chemistry definition. The study of quantities as it relates to chemical reactions. Quantities, how much something is, and chemical reactions. We just had a test over that, Unit 9. We know all about chemical reactions now, or we should. So we are quantifying chemical equations, which are reactions. All right, so here's a chemical equation that we should feel comfortable with. We have nitrogen plus hydrogen yields ammonia, NH3. Yes, it is balanced. If you want to check, please do. Now, we can interpret chemical equations many different ways. One way is molecules. What is a molecule? A molecule is one or more atoms in a bond. So, nitrogen, we have two molecules right here. N2, there's two molecules. How about hydrogen here? We have 6 molecules. How about ammonia? We have 2 molecules of ammonia, NH3. So there's one way to interpret a chemical equation, by molecules. Let's look at another way we can do it. Mass. Now, when you think mass in chemistry, that means we're going to be measuring in grams. G for grams, G for grab your periodic table. What are you going to use that periodic table? The molar mass. Nitrogen on the periodic table is 14.01 grams. Well, there's 2 of them. Multiply 14.01 times 2 or add it together, you get 28.02. How about hydrogen? Hydrogen is 1.01 on the periodic table. Multiply that by 6, we get 6.06. Now let's go look at ammonia. Ammonia is nitrogen plus hydrogen's molar masses added together times 2 because there's 2 of them. So we get 34.08. Now, if you recall the law of conservation of mass, that atoms, matter, nothing can be created or destroyed. So if we have the same atoms on the reactant side, we have to have the same on the product side. And look at those masses. They are exactly the same. And this is the case for every chemical reaction. So we can interpret a chemical equation by using mass, straight off the periodic table. And I've already said this. Mass of reactants and products are always equal. Please feel free to pause this video anytime. I hope you know that if I'm going too fast. This is at-home lecture, so you're welcome to pause, rewind, to listen to my beautiful voice again. Okay, so another way to interpret a chemical equation is by moles. Now, what is a mole? Do you remember the mole? Does that sound familiar? It should, because Unit 8, we talked about the mole. Do you remember Avogadro, that beautiful, wonderful guy, Avogadro? Well, he has a number, right? 6.02 times 10 to the 23rd atoms, molecules, or formula units equals 1 mole. So we're talking about the mole again. Now, using the coefficients in front of each atom or molecule in a chemical equation, we can use something called the mole. So I have 1 mole of N2. I have 3 moles of H2. I have, guess what? 2 moles of NH3. The mole is not some difficult concept. The mole is simply a unit of measurement. It's a unit of measurement for amount of substance. So it's amount of particles in something, the amount of stuff in something, in everything. We measure that by saying moles. 6.02 times 10 to the 23rd equals 1 mole. It's just like saying there's 12 inches in 1 foot. It's just a conversion. It's just a unit of measurement. So don't freak out with the word mole. So we have 1 mole of stuff of N2 here. 3 moles of H2. 2 moles of NH3. Now that's exactly what we're going to be focusing on in this unit, is moles and how to interpret a chemical equation. So the coefficients, meaning the number in front of the atom or molecule, in a balanced equation represents the smallest whole number mole ratio between reactants and products. The coefficient is what we use to balance equations. You've been balancing equations for a while now. Do you remember the tally system? Make sure the left, the reactants, matches the right, the products. If they're the same on both sides, you have the smallest whole number of a balanced equation. It's the same thing from the mole ratio. So balance an equation correctly, and then you can use your mole ratio. And let me show you what I mean. Here's that beautiful example. Again, we've been using nitrogen plus hydrogen equals ammonia gas. Here, boxed in red are coefficients, right? Well, it's also moles. We've already talked about that. So we can use mole ratios. What's a ratio? Ratio is just comparing 2 or more things. So I can compare nitrogen and ammonia for my first example here. For every 1 mole of N2, there are 2 moles of NH3. Let's look at this one. For every 3 moles of H2, there is 1 mole of N2. How about another mole to mole ratio? For every 2 moles of NH3, there are 3 moles of H2. All I'm doing is comparing moles to moles by using my coefficients. And that's exactly what the coefficients are, is a mole relationship. So knowing this information, I can answer questions. So for number 1, if 3.86 moles of potassium reacts completely with excess water, how many moles of hydrogen would be produced? That's a lot of words. Can I write a chemical equation from that? Sure. We have potassium reacts, so that's a reactant, completely with excess water. That's also a reactant. They're reacting together. So I can put potassium plus water for my reactants. Well, it tells me that hydrogen's being produced, but because I know how to do chemical reactions from Unit 9, I can write these as products. I can write a chemical equation. Water can be written as hydrogen hydroxide. So this is a single replacement. Would potassium beat up hydrogen, steal its lunch money, and replace hydrogen? It sure would. Potassium is more reactive on the activity metal series sheet that we gave you. So we would have potassium hydroxide plus hydrogen. Now we need to write the chemical formula. So we're going to ask those 2 famous questions again. Potassium, is it a metal or a compound? Excuse me, is it an element or compound? Yes. Is it a monatomic or Brinkelhoff? Potassium is monatomic. So we just write K. How about hydrogen hydroxide? Well, it's water, it's H2O. If you didn't know that, it's a compound and it's molecular, so you just use your prefixes. Dihydrogen monoxide. Let's keep going. Potassium hydroxide. It is an ionic compound, which means you have to show your charges. So potassium is a +1, hydroxide is a -1, crisscross applesauce, we get KOH. Hydrogen is a element, and it is Brinkelhoff. So we can write a chemical equation with words. We can give us the formula from those chemical words, and then we can balance it. And if you need to use your tally system to do this, please do. So I forgot what we're going after now. What was the original question? So I set up my problem correctly. I now have a chemical equation and it's balanced. So that means I can use my coefficients for moles. My question asked, how many moles of hydrogen would be produced? So what do I know? I know I have 3.86 moles of potassium. What am I looking for? Moles of hydrogen. So I'm going to have to use that beautiful, wonderful, awesome thing, dimensional analysis. Circled in red here are my mole to mole ratios that I'm going to use because I have moles of potassium. I need moles of hydrogen. So I can use that mole to mole ratio. So always start with what you're given, 3.86 moles of potassium. Well, I don't know what to do exactly. I'm a little confused. So what could I know I have to get rid of moles of potassium, right? So is there a conversion I could use to get 2 moles of hydrogen perhaps? Well, for every 2 moles of potassium, there's 1 mole of hydrogen. So if I put moles of potassium on bottom and moles of hydrogen on top, I can use that conversion in dimensional analysis. Now I have moles on top, moles on bottom, they'll cancel out, leaving me moles of hydrogen. So let me talk about this step again. I used a mole to mole ratio. For every 2 moles of potassium, there are 1 mole of hydrogen produced. So let's double check to make sure that we have our dimensional analysis canceling out. Moles on top, moles of potassium on top, moles of potassium on bottom. I'm left with hydrogen. Go ahead and plug and chug in your calculator. 3.86 divided by 2 gives you 1.93 moles of hydrogen gas. I have 3 significant figures given to me in my question, and I have 3 significant figures in my answer. This is the correct answer. Make sure you label. Let's do one more. How many moles of aluminum will react with 5.12 moles of hydrochloric acid? I'm going to go a little faster this time setting it up. So I have aluminum reacting with hydrochloric acid. Hydrochloric acid can also be called hydrogen chloride. If you don't know that, it's an acid. Just ask me or Mrs. Flint, and we'll tell you. Would this aluminum single replace hydrogen? Is aluminum a more reactive metal? It sure is. So I would get aluminum chloride plus hydrogen. Aluminum is an element. It's not Brinkelhoff, so it's just Al. Hydrogen chloride would be HCl because it's 1-to-1, mono. Aluminum chloride is ionic metal, so you have to show your charges. Crisscross applesauce, you get AlCl3. Hydrogen is Brinkelhoff, so H2. Go ahead and balance it. And if you need to use your tally system to do that, please do. Don't try to do this in your head. If you don't trust yourself, use the tally system. That is an efficient way to make sure you have a correct balance equation. Because if it's balanced incorrectly, your mole to mole ratios will be wrong and your final answer will be wrong. So let's write down what we know. We know we have 0.512 moles of hydrochloric acid. We're looking for moles of aluminum. So I'm going to be using the mole to mole ratio between aluminum and hydrochloric acid. For every 2 moles of aluminum, there are 6 moles of hydrochloric acid that react. Or you can say it the other way. For every 6 moles of hydrochloric acid, 2 moles of aluminum will react. So write what you know, 0.512 moles of HCl. I need moles of HCl on bottom, so I'm going to say 6 moles of HCl for every 2 moles of aluminum that's produced. They both cancel out, 1 on top, 1 on bottom. I'm left with moles of aluminum. That's exactly what I'm looking for. So multiply 0.512 times 2, then divide by 6, and you'll be left with 0.171 moles of aluminum. That's exactly what I'm looking for. I have 3 significant figures given to me. My final answer has 3 significant figures. I labeled my units, moles of aluminum. You are done. Pretty picture. Go ahead and start your worksheet. If you have any questions, let me or Mrs. Flint know.